All right. All right. So we are continuing in our quest, our ending quest to disprove entanglement. All right. So let's continue where we left off last time.
my reaction. The technical name for this more ordinary connection is called hidden variables. So the question is, how do we know that there's something new and different about quantum mechanics? How can we test the idea of quantum entanglement and compare it to the more intuitive idea of hidden variables? There's a long history of this, with a prediction in 1964 by theorist John Bell and a test in 1981 by Elaine Aspect, as well as contributions by many others. I'm going to forgo the history.
So, as I was saying last time, he seems to misunderstand. I mean, these two blue and red balls, I would say, have nothing to do, almost nothing to do with the question at hand. So, our question is a magic trick, right? So, no one is talking about information being transferred faster than light with the two balls. So, that's not the same problem. So this is, right, the problem is, how is information traveling faster than light? Obviously, that's a magic trick. So Einstein said the answer to this is hidden variables. And Einstein, I believe, was right. So I have a way to reproduce this magic trick with Einstein's principle of hidden variables. Let me show you. Well, I'll show you in a minute. We're going to write a Python program and we're going to reproduce this experiment, right? But let's first understand the magic trick. This is, right, why do we need to say that there is a magic trick that we're overcoming the speed of light limitation? Why am I saying that? Where is, right, what is he talking about? Why is he bringing up the speed of light in this discussion? Why am I saying that this is a magic trick? What's going on? Why is the name here spooky action at a distance? What is entanglement? What's so crazy? What is going on that is supposedly is crazy? Why does he bring up a picture of the entire earth? And what are these crazy arrows? What is going on here? So, okay, let's first understand the problem. So we have two particles that we believe, and I accept this. We're gonna assume this is correct because we're assuming that angular momentum is conserved in the universe, meaning assuming we had a parent particle that was not spinning, the spin was zero. So if this particle decayed into two daughter particles, then the total spin of the two combined must be zero. Therefore, if one of them, or if they're spinning, they must be spinning in exactly equal and opposite directions, and or what we call vectors. All right, that's a given. We're going to go with that. That's a nice assumption because I believe in a mechanical universe and this fits perfectly my assumptions, and it seems to be everyone's assumption. So that we're going to continue with.
Pointing left, the other is right. If one is up, the other is down, and so on. When you add the two, you get the zero that you started with.
Now, this is the actual particles, and we can never know what the actual particles are doing. That's we can't know exactly what the actual particles are doing because when it comes to a quantum particle, we just can't see them. Now, with your iPhone, you can't really know everything about your iPhone. You think you can, but really you can't. For example, you're not seeing your iPhone right now. You're seeing your iPhone with a slight delay because of the speed of light. And by the time the light reached you, your iPhone has already decayed a little bit, and so on. So it's difficult, and your iPhone is always vibrating. And anyway, and internally, of course, anyway, so it's difficult to nail down things in this universe. This universe is um, um, the way it's the fabric of this universe, the fabric of reality is difficult to pin down. That's a given. So the same goes, of course, for a quantum particle, where we can basically at this point we can barely see them. So okay, so the particles we're going to assume are definitely spinning with an exact equal and opposite, some exact and equal opposite direction. But there is some direction, but we're not ever going to know that direction. That for now, we don't have the technology to figure that out.
So that's the simplest example of a pair of entangled particles, which is to say two particles with opposite spin and a single wave function that governs both of them.
Now, when he says entanglement, entangled, and single wave function, that is utter nonsense. All you need to know is these two particles were created from a single particle that decayed, and therefore, as we said, the combined angular momentum of the two daughter particles must add up to the original angular momentum of the parent particle. So if you want to call that angular, if you want to call that entanglement, if you want to call that wave function, you can call it whatever you want. I don't think it has anything to do with a wave, with a function, or with entanglement. Maybe you could say they are entangled, like that's one word that explains how, okay, we could use entanglement to mean that, I guess. Fine. But unfortunately, the word entanglement has already been overloaded with magic. So I would, maybe I shouldn't use it, but you know what? Maybe we should. If I say entanglement, then you might not understand, because you might think that I believe in the entanglement that they believe in. Now, they believe in a magical entanglement that I don't believe in. So I'm just not going to use entanglement. I'm just going to say entanglement doesn't exist. And when I say that, I mean their belief in entanglement. Whatever they believe entanglement is, that is nonsense. The word entanglement in the dictionary, that's a word, it's a good word. But quantum entanglement, the way they believe in it, the way they teach it, is total nonsense. Even definitionally, they say it makes no sense. So they agree it's nonsensical. So it's nonsense. So I'm going to avoid using the term known as entanglement. All right. Instead, I'm just gonna repeat every time whatever I want to repeat. Anyway, let's continue. So,
Okay, so now we're getting somewhere. The entanglement doesn't depend on the two particles being close to one another. As long as the two particles don't interact with anything, you can separate them by feet, miles, or even huge distances.
and when he says entanglement, I'm just gonna say the total angular momentum is equal to zero. Let's assume that the parent's angular momentum was zero, so the total angular momentum is zero. And it doesn't matter how far you separate the two daughter particles.
And the two particles are connected by a single wave function, and the two.
That's nonsense. The total angular momentum equals to zero. That's all. That's all we know. That's all we need to know. Everything else he says is utter nonsense. It literally makes no sense.
Particles will have opposite spin. Now, remember that one of the key facets of quantum mechanics is that the quantum world is intrinsically probabilistic.
That's utter nonsense. That's true for the universe. The universe is probabilistic. That's just this universe. Meaning anything you do is probabilistic. Is the sun going to rise with a certain probability? Right? Everything in the universe has a probability attached to it. It's never zero and it's never one. It's always in between. Everything.
We can't know, even in principle, the outcome of a measurement
That's true for everything in this universe.
before we make it. So
That's true for everything in this universe.
suppose we select one of the two particles and pick a direction to measure the spin. Say we pick horizontal. The measured spin will be.
That's true for everything in this universe. When you want to measure, you pick a measuring device, you create a measurement protocol, meaning the steps you're going to take during this test, the test description, the actual test. So the test script. So you come up with a test script, with a test protocol, with a test apparatus, whatever it is, and you get a test result. That's true for everything in this universe.
either right or left, each 50.
So you come up with a test. You're going to test, did the car take a right or a left turn? Did the particle go up or down, right or left? Did I, whatever it is you're measuring, you're going to measure what did it do. Happens to be with spin. The only thing we can do with it is measure, did it go up or down relative to the magnetic field, or right or left? Did it go in one direction of the magnetic field or the other? With the magnetic field, there's either north or south. Did it go north or south magnetically? However, we created the magnetic field.
50% of the time. We could have selected the other particle to do the measurement with the same result, 50% right and 50% left.
So since we don't know which way the daughter particle 2 is spinning when we test it in the right and left direction, we have 50% chance of getting it to the right, 50% chance of getting it to the left.
The real weirdness arises when we measure the spin direction of both of the entangled particles. Say we measure.
Now here is the magic trick. Here is where he's going to pull a fast one on you.
The horizontal spin direction of this particle over here on the left, and the measurement says it's to the right. Then we know that the outcome of the other measurement.
Okay, so we measured particle 1 and we discovered it's to the right. Now when we measure particle 2, what will we measure, right? We said that there's no way to know what we're going to measure before we measure it. But in this case, it's always that it's going to be to the left. If we know that the first particle measured to the right, then we can predict with 100% certainty that particle 2 will measure to the left. How can we do this? How can we be sure? We said that we cannot know the result of a measurement before we do the measurement. But in this case, we know. And he's going to say it's the magic of entanglement, of a single wave function, and the rest of the nonsense. Obviously, that's nonsense.
100% of the time.
I'm not saying it's nonsense. He says it's nonsense. They say it's nonsense. They say it makes no sense. I'm not saying anything. I'm saying it's a fast one. It's the hand, like it's they're fooling themselves too. But it's just a magic trick, and we're gonna hopefully I'll be able to repeat the magic trick, and you'll see it's just a magic trick.
Left 100% of the time.
So when we measure particle 1 to the right, we will always measure particle 2 to the left. How could that be? Remember, when we measure particle 1, there's no reason it should be to the right. All we know is that, as far as we know, the assumption is that particle 1 was spinning towards the right hemisphere of the universe. If we split the universe down the middle, horizontal, like through a vertical, imagine a vertical plane going through the arrow of particle 1. So if our detector says that the particle is spinning to the right, what do we know? Actually, we don't know anything. The particle might have been spinning to the left. Right? A particle that is spinning almost to the left, 1% of the time would be detected as spinning to the right. That's the way. That's our assumption. Since no one ever saw actually what happens, but logic dictates, this is just a logical inference, that from the detections, since every time we measure a particle we get 50%, The particle could have been pointing anywhere. It could, except for we all we know is it definitely was not pointing at the left. Because if it would have been pointing exactly at the left, then it cannot give anything but a left result. If it gave a right result, then it might have been pointing anywhere. Right? It might have been pointing to the right. It might have been pointing a little bit off the right. It might have been pointing exactly up, in which case 50% of the time it would detect to the right, but it might be pointing almost to the left. Because if it's pointing almost to the left, some of the times we still get a detection to the right. That's our assumption. However, right, so it might have been pointing almost to the left, which means the other particle is pointing almost to the right. Almost to the right. But we know
Then we know that the outcome of the other measurement, it will be 100% of the time left, 100.
to the left. So it could be that the first particle was pointing almost to the left. Almost to the left. But it gave us a reading to the right because it's the nature of the game is that it gives us probabilistic results. That's fine. We can live with that. That's the mechanics. That's just the given mechanics. That I can live with. For some reason, for some peculiar reason, sometimes, right, as we say, anything that can happen will happen. Right? You don't know. Like you wake up in the morning, you don't know if you're gonna survive getting out of bed. Who knows what's gonna happen? Because sometimes crazy things happen. One second. I have to go soon. Okay. So it could be that the particle almost pointed to the left, yet we got a reading to the right. Now, if it's pointing, let's assume it was pointing all the way to almost all the way to the left. Well, the particle 2 must be pointing almost perfectly to the right. Yet, we know 100% of the times that we're going to get a reading to the left. How could that be? Now, if you would say, well, this right, so this particle 1 flipped a coin, right? Let's imagine particle 1, right? It looks like particle 1 flips a coin and decides how to be detected. That's how it looks because it's probabilistic. Okay. So you would say, let's ask the question, how is it? Okay, so let's try and tell the story of what just happened. So particle 1 so particle 1 flipped a coin and decided to be detected to the right, which is obviously is ludicrous, but let's go with it. We have to come up with some ontology of what the hell is going on here. So let's say particle 1 flipped a coin and decided to be detected to the right, even though it was almost perfectly aligned to the left. Let's assume this is the story. Okay. Now, particle 1 wants to let particle 2 know. Let's assume this is the story. Particle 1 wants to let particle 2 know, hey, I just decided to be detected to the right, even though everybody knows, I was pointing almost perfectly to the left. And I know that you are aligned almost perfectly to the right. But since we want to be observed as entangled, we want people to claim that there's a magical universe, then I want you, we want as a family, because we are daughters, sisters, we want you, particle 2, to be detected to the left, even though you're almost perfectly aligned to the right. But you have to keep appearance. Keep the appearance. So particle 1 transfers the information. Of course, it's done telepathically because particle 1, particle 2 share a telepathic communication because these people are completely nuts. They literally believe in ESP. They literally believe it. If particle 1 is entangled with what they say it's the same wave function with particle 2, then why can't this happen between two individuals? Why can't we share thoughts telepathically, instantaneously across the visible universe interdimensionally? Why not? Why not? Why not? Let's go nuts. Let's go nuts. All the way nuts. This is like the ancients who used to believe crazy, bat shit, crazy stuff. Same. Nothing changed. So you think something changed? Well, think again. You got another thing coming. You haven't seen nothing yet. You ain't seen nothing yet. Nevertheless, let's continue. Let's continue down this rabbit hole. Anyway, zo, 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 zo. So particle 1 sends an ESP, extrasensory perception, telepathic message to particle 2. Of course, particle 1 is an intelligent creature. It's actually an angel. It's an angel of the gods because, of course, we believe in the gods. Did you think? Did you think any less? Did you think the gods are not going to get involved in this discussion? Well, think again. You have another thing coming. So, particle 1 sends a telepathic message to particle 2, who is also a super intelligence. These are super intelligence because we live in the matrix, you see. So particle 1 sends a telepathic message to particle 2. Now particle 2, pointing almost perfectly to the right, gets the message that says you have to pretend that you're pointing to the left. So you have to be detected to the left. And by the way, remember particle 1 decided to be detected to the left. And to the right. So remember, particle 1 decided, it literally flipped a coin. No less. It flipped a coin. And it looked at the coin and he saw the coin says, be detected to the right. How did particle 1 know? And don't ask questions. You're not allowed. If you ask questions, oh my God, if you ask questions, how dare you ask questions? You don't believe in science. You think you're smarter than Einstein? Einstein was wrong. Even Einstein was wrong. And you think you're smarter than Einstein? You think you're smarter than Sean Carroll? You think you're smarter than the doctors and the professors of Fermi Lab? You think you're smarter than all the geniuses from the past 100 years? You think you're smarter than them? You don't even know anything. You just started studying physics. How dare you? How dare we're going to silence you. We're going to silence you because we know you're wrong. So we don't need to debate you. We don't need to debate you. We can silence you. That's even better. We can silence you. How dare you? How dare you? We don't want to know. We don't want to know. This is Plato's cave. We don't want to know. We're going to silence you. We're going to remove your eyes and we're going to cut your tongue off. Stop talking. Stop telling us what's outside. We don't want to know. We're happy living in the cave. We're happy believing that the shadows on the walls of the cave, that is reality. We're happy with it. We don't want to know anymore. We don't want to know. Shush. Shush. Somebody stop him. Somebody stop him. He's threatening the status quo. Everyone knows the status quo is holy. He's threatening to change what is not he's threatening to make changes. We don't like changes. No, don't let him make changes. No, we cannot allow changes. Shut him up. Welcome to Plato's cave, where we shut everyone up if they don't toe the party line. Welcome. Welcome. Anyway, so according to this magic trick, so particle 1 felt a magnetic field and had to decide which way it's going to go, with the magnetic field or against the magnetic field. Now, let's assume it was pointing almost perfectly to the left. Let's say it was pointing at, you can imagine a clock, right? Right now, particle 1 is pointing at 3 o'clock. Let's assume it was pointing almost at 9 o'clock. Let's say 9:01. It was pointing at 9:01 on the clock. So almost perfectly to the left. But it flipped a coin and decided, today I'm going to move with, there's no with, I'm going to move, let's say, to the north. Let's assume this is the north of the magnetic field. Today I'm going to move to the north of the magnetic field. Another day, maybe particle 1 would have flipped a coin, and according to the coin, particle 1 would have gone to the south. But today, particle 1 decided. Now, the flipping of the coin is determined. I mean, the flipping of the coin gives a 50-50% chance, but the direction of the actual direction also, it weighs the coin. It manipulates the coin, but still there is a coin toss. As particle 1 is more perfectly pointing at 9 o'clock, so it becomes 100% chance that particle 1 will flip a coin and the coin will have to take it to the left. But when the particle is not perfectly aligned with 9 o'clock, when it's at 9:01, then let's say there's a 1% chance, right? Still there's a coin flip, but the coin flip is only for the 1% chance. 99%, it's a coin that is not balanced. It's 99% heavier to the left than it is to the right. It's like when you have a piece of bread and you spread a lot of peanut butter and a lot of jelly, so it becomes very top heavy. So if it falls, it's always going to fall 99% of the time. It's going to fall on the jelly, smack on the floor. Why does that happen? Because it's not a balanced coin. So as the particle's actual direction determines the weight of the coin. If the particle is pointing perfectly to the left at 9 o'clock, then the coin is 100% weighed to the left. But let's say the coin is weighed only 99% to the left because the particle is pointing at 9:01. And the coin is flipped. Particle 1 flips the coin. And particle 1 gets, against all odds, is being told by the coin, you have to move to the right. You have to move this, let's just say this is the north and that's the south. You have to move to the north. So particle 1 obeys, which on its face is ridiculous because particle 1 doesn't decide. How can particle 1 decide? Well, particle 1, what does it mean to decide? Even humans don't decide. What does it mean to decide? Even we humans, we don't decide. We follow our reason. if I see a hot chick, I'm going to do what she says. Not because of a flip of a coin, but because the hot chick says to do something. So that's us. That's humans. If I so and whatever she says, I do. So, but uh, the particle, I don't have a choice. When a hot chick says to do something, I do what she. I don't have a choice. I'm like a pebble rolling down the hill. I don't have a choice in the matter. I just do what she says. That's a given. And same too for a particle. A particle doesn't have a choice. Particles obey the laws of nature, just like I obey the laws of hot chicks. Nevertheless, nevertheless, let's continue. So. So the coin, so the particle one flipped a coin. It flipped a coin. And the coin is 901. Sorry, the particle is 901. So the coin is 99% way to the left, but still, particle one flips the coin. And the coin says, go to the right. And the particle one goes to the right because it's being told it cannot disobey what it's told by the coin. The coin rules. Okay. Now, particle two, if this happens, right, there was a coin toss, particle two, far away on the other side of the galaxy, cannot know that this happened. There's no way, right? It's going to take the information, it's going to take it trillions and trillions and trillions of years before the information. Trillions? I don't think it's going to take trillions. I think it's going to take just about 100 billion years. But by that time, particle two is going to be outside of the event horizon. So the information can never reach it. Nevertheless, particle two somehow, using telepathy, of course, because there is telepathy, everybody knows. So particle two receives a telepathic message that says that particle one chose to move to the right. Particle 2 then knows it must move to the left. It's as if the same coin, it's as if the same toss of the coin tells both of these particles what to do. Tells particle 1 to move to the right and particle 2 to move to the left. However, the information could not have traveled. So how did it happen? And this, we're told, this always happens. And this really bothered Einstein. So that's not true. This did not bother Einstein. This absolutely did not bother Einstein.
Percent of the time. That means that the information that one of the two particles had a measurement made on it was transported to the other particle. And here's the spooky thing. We can measure the spin direction of the two particles in quick succession, so quickly that we measure the second one before any conceivable information from the first measurement could have arrived. Let's be super concrete on this by remembering that the fastest thing in the universe is light. It travels a foot in a billionth of a second. Now, let's take two entangled particles and separate them by 10 feet. It will take light 10 billionths of a second to travel from one to the other. So now let's get tricky. We'll measure the horizontal spin of one of the two particles and see that it's to the right. Then 5 billionths of a second later.
So there's not enough time for the information to reach particle 2.
We measure the horizontal spin of the other particle. We find 100% of the time that it's to the left. And
how? But there wasn't enough time for the information to arrive at particle 2.
And remember that we did it so fast that not even light could have told the second particle the outcome of the measurement of the first particle.
So we know that it cannot be that the information was shared in real time. Did you hear what I said? That's the hint to the answer, to the magic trick. Let's see if you got it. Let's continue.
That means that quantum information can travel faster than light. Yeah, you heard me right. Faster than light. That blew Einstein's mind, too.
No, it did not. And I know it did not, and I can prove it.
In fact, he co-authored a paper in 1935 with Boris Podolsky and Nathan Rosen that highlighted this problem.
He did not. I don't know what he did. I don't care about this paper. He did not. His mind was not blown, and it did not bother him.
We'll call this transfer of quantum information spooky action at a distance. This was one of many reasons why Einstein didn't like quantum mechanics.
Einstein never said I don't think he didn't like quantum mechanics. He didn't like the Bohr interpretation and your interpretation of quantum mechanics. It's obviously ridiculous. It's obviously nonsensical. Not that I say that it's nonsensical, not that Einstein said that it's nonsensical. It's that you say that it's nonsensical. You claim it makes no sense.
So what do we think about this phenomenon today? Does quantum information move at speeds faster than light? Yeah, it seems to. But it doesn't invalidate Einstein's theory of relativity
Yes, it does. It literally does.
because we can't control it. We can make both measurements and the outcome will seem random, and we'll only know that the two were opposite when we compare the measurements, and that information can be transferred no faster than the speed of light. So that saves Einstein's theory, which is a relief.
No, it doesn't.
Otherwise, I'd have to learn a whole bunch of physics.
Yes, you do. Yes, you do. You, of course, you do.
But it's still perplexing.
I mean, you can laugh it away. Oh, so it's still perplexing. Oh, but it's still perplexing. You just laughed it away, but it's still perplexing.
How is it that quantum mechanics can travel so fast?
Wait a minute. Are you confused or are you not confused?
Well, there were some people, including Einstein, who thought that this wasn't so mysterious after all. Suppose
So which is it? So which is it? Was his mind blown? Or did he think it's not mysterious after all? Which is it?
you had a red and a blue ball, but you couldn't look at them. You grab both of them and put them in boxes and separate the boxes. Later, you look in one of the boxes and see that it contains a blue ball. It will surprise nobody that the other ball is red. The answer was determined at the moment the
Yeah, this is not exactly the solution, but it's close to the solution.
balls were put in the boxes, not when the first ball was observed.
And that's Einstein's answer. Einstein was not perplexed by this. This is very simply explained. I'm perplexed that you're perplexed by this. And I guess Einstein was perplexed that you're perplexed, that Bohr was perplexed. What is there to be perplexed about? Like, I'm perplexed. You're not dumb. You're not dumb. How could you be perplexed by this? It's a simple magic trick.
And I admit,
Oh my God, look, there's code 6743176. Jesus Christ. Don't forget Yuli's goodbye cake, 2:30 p.m. This is like the epitome of big office. It's like every day somebody has a goodbye cake. Report on quantum gravity due September 1st. I love reading all these notes. You are here. Oh my god. Oh my god. This is like, what is this? Oh my god. Is this good enough? Oh my god. These are so funny. Single muons, single isolated, 3 jets total. Theoretical precision. Oh my god, this is so funny. Cleanup. Oh, look at this diagram. There's a Z boson. Confusion possible? Question mark. Charge something. Neutrinos? I don't know. Jet mass? Anyway, S equals 1/4 A. Black hole. Data law arbitrary. 1A. Supersymmetric particles. E Tuft. I gotta run to the bathroom. I gotta poop my pants. Read out. Okay. Let me do a bathroom break. Where's the bathroom break? Bathroom break, bathroom break. I need to poop my pants, bathroom break. I need to keep this bathroom break available at all times. So this bathroom break done. Okay, here is a bathroom break. We'll be right back. All right. That was a long break. And soon I have to go. I must to go. Hmm. Okay. Let's see. Hi. When was this? Oh, this is half an hour ago. I'm wondering what I should do. Should I restart the stream or yeah, let's restart the stream. Yes, I think we should. Let's close the stream.